It's bad.
Yeah. So in Git Hacker Edition, one of the things that you kind of should understand at some point in time down the line is if you want to spin up products and you want to get things working quickly, the best thing to do is build on the existing tools of others. All right. So for those who don't know who Scott is, Scott also works at GitHub. Scott is a professional. He basically does PR for them, a lot of things, and he goes around the country giving this talk, talking about why Git is wonderful. It's hosted in a Git repository on GitHub. It's been crowdsourced to be one of the better talks to introduce people to Git a lot. So more than anything else, I'm just going to give his talk. It's a very good talk. Skip through the beginning a little bit, because it's a little less interesting to the crowd. But the gist of it, largely, is going to be what it is, how you use it a little bit, and then it drifts a lot into how Git works under the hood, a little bit of understanding about the Git object model and how everything kind of plays together. And then you drift back out to how to use Git, related to how things are working under the hood, and hopefully you get a better understanding of what's going on. One of the bigger grievances with people who are new to Git, beginning with Git, etc., is it's a little bit cryptic, and that's being generous. It is the Swiss Army knife of version control, but you have to figure out where all the little tools are, and it takes a little bit of time. Okay, so kind of rolling into it. What is it? Git is an open source distributed version control system designed for speed and efficiency. And if I was giving this talk as a professional, that'd be the most important part. But really what you care about is its version control. All right, version control is a wonderful thing. You want to use it a lot. You can grab it for free on the webs. Great. It's distributed. All right, distributed is a different idea that. All right, let's get a survey of the audience where everybody is. Who has used CVS? Okay. Who has used SVN? Who has used Perforce? Who worked at Microsoft? Amazon. That's close. Let's see. Who's used Mercurial? All right. All right. Who's used Git? Wow. Well, fuck. All right. Going through the beginning of this talk a little faster now. Ooh, who's used Bazaar? No Ubuntu love in the crowd. All right. That's fine. Yeah. So clearly you have a pretty good idea of what's going on in the beginning, so we'll kind of rock through it. Fully distributed. Almost everything is local on your machine, which is great. What it really ends up meaning is that everything is very fast. And the other thing that's a huge advantage that often gets neglected is that every person who is working on your project, every person who has cloned your repository, is acting as a backup. All right? So if you're working on a school project and the three of you are just sharing on your laptops, you still have nice 3-copy replication. You don't have to have some fancy hosting somewhere. Although GitHub gives it to you for free, so great. This is actually a really, really, really nice feature. And you can work offline, great, fine. All right, it is designed for speed and efficiency, and one of the things you'll see a little bit later on as we talk about how it works is there's a lot of trade-offs. It is designed for speed, and it is designed for efficiency of usage. It's certainly not designed for efficiency of resources. It eats memory, it eats disk, it eats everything else. But it turns out nowadays those are all cheap. The only thing that's not cheap is developer time. So it's optimized to make things work well for you. All right. And the last little feature of it that's quite nice, that was a tucked in there, is that it's immutable. That is, it almost never removes data. All right. The whole idea is you're moving forward and you can always get back to data that exists in the past. So, for those who are a little familiar with version control, how it traditionally works is it works on a patch-based model. That is, you start with a file and you make some changes and you just save the changes, right? Brilliant. This is wildly efficient. Computer scientists love this, because now we have a nice little directed graph we can go through and be like, all right, I started with file A, I've got this delta, and to get to commit 3, I have to apply 1 delta to file A, 2 deltas to file C, and you can work through this whole thing, and you can see how you can start from this beginning, apply all these deltas, and end up with a thing. And it's this really elegant, small, compact format. All right? But what does this save you in practice? In practice, this saves you disk space. All right? And it turns out we don't really care about that anymore. All right? What we care about is time. So what Git does instead is snapshot storage. It actually saves just whole copies of the file. Just go nuts, right? It saves copies of the file everywhere. Make a change, save a whole copy of the file. Save the original, save the new one, save them all. So you can kind of see what they're going at with the dashed lines here is these two files are exactly the same. So there's only one copy of these saved. You don't need 2 physical copies of them. However, this file A, which may have only very small deltas, there are still 3 copies of that file on your disk. All right? It is a slightly different idea. And again, the idea here is going through deltas takes a lot of time, it's a lot of computation, particularly as you're looking further on in the future, right? If you want to jump from commit 1 to commit 1000, you have to do a lot of computation in a delta-based system. If you want to jump from commit 1 to commit 1000 in a system like this, it's a series of move operations, right? And it turns out move is really, really fast because you're not actually copying any data, all right? all you're doing is renaming and changing pointers really fast. All right? How is this different? It is fast. So that's how it's fast on disk, and this is how it's fast kind of in everything else. Right? When you're performing a diff, it's comparing local operations that are already on disk. You don't have to go out and ask some server what were all the deltas, amalgamate all the deltas, put them all together, and come up with this complicated diff. It just exists. You run the diff program and file here and file there. Done. All right? You can see histories right on disk. You can commit changes right on disk. You can merge branches right on disk. You can change any older versions of files. You can hop between branches. You can do everything. All right? So as an example of why it is so much faster, if you want to check out the jQuery project, all right, and you did it in Git and you did it in SVN, Git's a little faster to check out. Great, okay? It's because it's a little less load on the server. You copy things down in one compressed file, big stream, call it a day. All right? Size-wise, Git loses, right? Git takes more space on disk. We are just giving up that one. However, if we want to say, look at our revision log, we are now 34 times faster because we are just looking at a file on disk. This is a huge win compared to bothering to go out, contact some central server there, negotiate a little security, to ask the server to look at its disk, do some computation for you, send back data. It's a pain in the ass. All right? Things get better. Now we start doing diffs. All right? If we do a diff between the original and the elite history, we can see Git kicks ass, subversion cries. All right? If you try and submit, wow, this will be recorded. I should probably watch my language. Brilliant. Anyways, if you do a relatively large commit of any kind, Git is going to win again because all it's doing is copying new files and calling it a day as opposed to doing any degree of computation or anything like that. All right? Huge advantages. You can work offline. You don't have any of these SVN directories floating around, and it's really cheap to branch. All right? So if we go through and we say, all right, if I have my Git repository, and I go into that repository and I try to check out a new branch, you know, how long is
What's a branch?
You all said you knew what version control was. That's why you get the fast mode of this talk. And we'll go into a great deal of what branches are and how they work. Checking out a branch, really, really fast. This is the motivation for Git part of the talk, which I don't need as much. That's why we're going fast, because you all use it, love it. All right? Really, really fast. Great, fine. As opposed to Subversion, how do you do a branch in Subversion? What does Subversion actually do when you create a branch? Anybody know?
Does SVN has branch each time?
Sure, SVN-branch is the term, but what does Subversion actually do?
I think it just makes a new copy of everything.
It copies the entire directory. That's exactly what it does. All right, it makes a whole new copy of a branch. It creates a directory called branch name and copies everything over. Essentially this, and takes much longer, right? So we can jump through easy merging, fine, how do I use it? If we're trying to get started, you install Git on your machine and you want to start off a little bit. So the first thing you do is you set your name, you set your email, and you get yourself a repository, all right? If we grab a repository and we want to start off with a brand new one, we're not writing to anybody else, we're going to say, all right, I have my directory, I'm going to create a file, fine and dandy, and I'm going to create a repository. All right, git init is the magical command that says, take this directory I'm in right now and turn it into a Git repository. And when you do that, turns out a lot of crap happens, all right? In particular, what happens is we have, this is our working directory right here, and we can see the hello world file we created a moment ago, and we can see this .git directory was made with lots of interesting things going on inside of it, all right? In particular, we can take a little bit at, here's our original file, here's our .git directory, all right? And we'll drill into what all these pieces of that are, we'll drill into what all the pieces of that directory are, and what Git is doing behind the scenes. First, however, we're going to grab a slightly more interesting project. We're going to grab one that actually exists. So as opposed to creating a new Git repository for your own work, you can grab one that exists out on the web somewhere. So we can grab the project of the original presenter of this talk. And you are free, if by default, this will create a directory called Grit, because that is the name of the project. You can make it any directory you want, like so. And it'll go through, it'll print lots of interesting things out. And basically what it's doing is saying, I made a directory called mygrit. I'm going to grab lots of stuff and do lots of math. We'll talk about what it's doing a little later on through the talk. If we go into this directory and we take a peek, we can see all the files are there. It's automatically brought us out to the most recent revision. And that's where we are. Okay. So if we dig into this Git directory a little bit, right after we had initialized things, we are going to see the first area of interest is the configuration. And we did a little bit of configuration a second ago when we added our name and we added our email to Git. All right? But Git, like any good Linux software, has the nice trifecta of configs. All right. The trifecta of configs, you'll find that pretty much all software follows this model. There exists a global config, an etc git config, or really for any program, there's something in etc that's going to configure for all the users of this machine, this giant global configuration, a nice set of defaults. If you want to have things that apply to all of your Git instances, all of your instances of any running program, you'll have something in your home directory. And then if you want to apply some specific settings to just this repository, you can put it in this repository's git config option. Okay. There are some other cool things. There are hooks. Who knows what hooks are? What are hooks?
Hooks are a way to tap into the inner core how the system works. So at any point during the workflow of whatever it's processing, in this case post-commit, post-receive, those are stages in the Git process. You have the ability to tab in and modify the inner workings without harming the core.
Yeah, so the general idea is they're basically glorified function callbacks, all right, if you want to think of them that way. Wherein Git is going to go through and do something at a certain point in time. An easy example is it's going to commit. At some point in time, you're going to commit something to this repository. And if you want to have something occur at the end of every commit, say for example you want an email to go out to your entire team that says, Johnny just committed to the repository these files, all right? Or a more useful one, you can have an automated test suite that runs and benchmarks or validates all the code, make sure you don't have regression testing, that's the word I'm looking for. You can have that run automatically, very, very easily, the idea of the hooks, all right? Objects. Objects are the heart of Git. All right, we're going to drill into objects in about 5 or 6 slides. And these things called refs. Refs point to objects. All right, and we're going to drill into exactly how all that works in a moment. So when we start off, we had this repository. We put a file in it. We initialized it. We added it and we committed it. And once we do all that, now we have stuff. All right. So we know that we have committed one time. We've committed one file, and we end up with 3 objects in a ref. Okay. We'll talk about what these 3 objects are as we go through these slides. And the reference right now, the master, which is currently the branch you are currently on, is pointing to one of these objects and is telling us where we are in the world. Does that all make sense? All kind of with me? Okay, cool. So your basic Git workflow is you're going to edit files, stage your changes, review your changes, commit your changes. Okay? So Git is composed, when you're working, of 3 things. You have the working directory where you live, this abstract notion called the index, and the repository. All right? So the working directory is where you live right now. All right? That's where when you checked out a copy of the repository, when you initialize a copy of the repository, there's just this directory. It's what you're LSing in, it's what you're editing files in, it's just the directory that's on disk. All right? The repository is that thing hanging out in the .git directory. It's the thing that's made up of objects, mostly of objects, with pointers into it of refs, whatever else. And it's not anything you interact with directly. All right? Git messes with the repository all the time. And the index is limbo. All right? So we'll see how the index is used in a moment. So when we talk about editing files, hopefully you all know how to edit a file. If we're in a directory, it is a Git repository, it has some files. And we go ahead and we edit a file. And we say, all right, this is my file, and I'm going to edit it to say, add a comment to let the world know that this program prints hello world. All right? Great. Very useful. People want to know what it's doing. I save, I quit, and I ask Git, what have I done? What have I changed? What does the world look like? And it prints out all this crap. It prints out a relatively large amount of information, right? Because I'm on branch master, there's changes, I'm modified, and got all those kind of weird things going on. All right? And then what it really wants to look at here is we want to see that we have modified main.py. Great. I believe I modified main.py. That's exactly what I wanted to do. But what does this line up here say? Changed but not updated. All right? This is part of where the weird beginning starts. All right? The better way to think about this is changed but not staged. Okay? So committing in Git is really 2 phases. The first thing you do is you stage a commit, or you stage a change to be committed, and then you actually commit everything. So it allows you to kind of organize your commit before you do anything. You can take all these files, you can add them to the staging area, you can add pieces of them to the staging area, you can get the commit looking exactly how you want, and then you commit in one big go. All right? So, the next steps along the line are staging the changes and reviewing your changes. And the way we do that is we do that with the git add command. So git add takes us from this model right here, where we have the working directory, we've edited a file in the working directory, and we're going to add it to the index. So the index is the place where everything is staged. All right? And it's important to know at this point that this is more of a conceptual difference. All right? So the index and the working directory physically look like the same place. All right, if you ls in a directory, the files are there. They're the same thing. The only difference is conceptual. This is in the Git model of the world and kind of understanding what's going on. So going back to the terminal, if we add main.py and we go out and look at it, we see the world has changed a little bit. Now we have modified main.py, but it's the changes to be committed. All right, this is a consequence of having run the add operation. Now what we're saying basically is changes that are staged, changes to be committed, changes that have been staged. Okay. So we've changed them, but we haven't actually committed anything yet. We haven't actually applied any of these changes yet. Go back to the terminal, edit another file. All right, here we are. We're gonna go from version 1 to version 2. Okay, great, fine. Save, quit, and I asked for the status. And now we end up with a slightly more complicated status. All right, but hopefully we can see the two parts of it that look more or less the same as they were before. And you can see where these two files, even though they're in the same directory on disk and look like they might be in the same place, are in two different states. All right? In the Git view of the world, they are in two different logical places. One of them is currently in the working directory, and one of them is currently in the index. Are you with me? Okay. Let's go a step further. Let us go ahead and edit main.py again. All right? We're going to go in and we're going to go, I speak Spanish. Not really. All right? And now we run the status, and now things are weird. All right? Because now we have the situation where the main.py file is both staged and not staged. And it turns out this is one of the most powerful and cool features of Git. All right? Git works on chunks of files. Git works on logical blobs. Git works on logical sections. Sorry. However you want to think about it. All right? So what you actually have is you have these files which are staged, these ones which are in the index, and these files here which are just hanging out in the working directory. All right? And main is really in both of them. So what you end up with is you have this dichotomy where the original file here is staged, that is the commit we have staged is in both of them. However, the working directory and the staged world say different things. All right? Everybody with me so far? So the file on disk currently says Hola Mundo. All right? The only place that this hello world line still exists is in this index, which is off in the ether somewhere. It does exist, but I'll tell you where there. All right. So, after you edit a file, if you want to actually save the changes, you need to stage it. After you edit the file, you need to stage it. All right? This is a concept that people have a lot of trouble with working with Git. So after we do this, we're going to go ahead and add, and now we go back to this view of the world where everything is ready to be committed. All right? So what we've done now is we've moved everything from the working directory into the index. And when we actually go through, the last step is to commit your changes. All right, the command here is git commit. Yes, I know. It's a great slide deck, isn't it? And much in the way that git add moves things from the working directory to the index, git commit moves things from the index to the repository. All right. So we'll note that git commit does not change the working directory at all. The only thing it does is it changes the repository. It changes Git's view of the world and changes your perspective of what you're doing. None of the files in the working directory have changed at all. All right? Looking at it in the command line view of the world, git commit. When you type commit, it's going to ask you for a commit message. Hopefully you're all familiar with commit messages. Who knows how to write good ones? Well, one person said yes, but I might actually believe, otherwise I was going to call you all liars. Changed main.py. That is exactly what you did. So there's lots of cruft in the bottom, and it's a really nice thing because basically what it does is it throws open your default editor by default. In this case, it happens to be Vim. And it has all these comments, and it tells you basically what you changed. Just a nice little reminder to yourself, just in case you somehow manage to forget. And you can put together a descriptive commit message. All right? If you have realized halfway through the process, most often when you skim the bottom down there and you realize that there are unstaged commits, unstaged changes, that you forgot something, you can just abort. If you don't save any changes and you have an empty message, it will quit and die, which is great. But if you let the commit go through, then you're going to have this wonderful message that says, I have created commit 77D3001 with the commit message, descriptive commit message. It changed 2 files, it added 4 lines, and removed 2 of them. All right? So as a basic workflow, you basically have, I edit my files, I stage my changes, I look at my changes to make sure they're exactly what I want to do, and I commit the changes. All right? This kind of looks like a lot of work, and you can cheat. All right? And the way you cheat is you edit the files, and then you do it all in one go. All right? All in one go is basically this magical thing that goes through and says, all right, we're just going to commit everything we need that has changed at all, and it's basically the subversion view of the world. All right? And for your basic changes, basic commits, it turns out this is pretty nice and fairly convenient. But when you want to do more powerful, more flexible things, Git allows you to do so, which is very, very nice. But let's stop and take it back a minute, and let's see what's actually going on here. Because as I mentioned a second ago, when we committed the very descriptive 77D3001. All right? And it turns out that is extremely descriptive. All right? And if we pull that out and we isolate it a little bit, it's part of a much longer hash. All right? And everyone here is cool with hashes, know what they are, know what they do. Yay, nay, nay, so. All right. The idea of a hash is basically if I take a large blob of information and I apply this magical function we call a hash, we can turn it into a fairly unique series of digits and numbers. All right? And Git's all about the hashes. It's in love. The security guys are laughing at my description of hashes.
Just the hash been fairly, yes.
Well, considering the source of data is not sufficiently high entropy, it's a relatively... Anyways, not going into security right now. So, it turns out what this thing is really doing is this is a hash of all the data in the commit. All right? And a commit composed of a few things. The commit is basically an object called a commit object. The commit object has a tree that it belongs to, has a parent above it, has the author, the committer, and the commit message itself are all the things that live in the commit object. All right? And we can see, if we look at it exactly, this is literally what is saved in the object. All right? So there exists a file on your system. That file is named 77D3001, etc., 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 and it contains that. All right? This is what it has. This is how the world works. This is it. The commit object is just a flat text file. It just lives in the least efficient version of Git, anyways. Anyway, it's just a flat text file. It just lives. It just exists. All right? And if we drill into this commit object a little bit more, we look at this tree thing. All right? And the tree thing is is in a way of expressing a directory. So the directory that is saved in your Git repository is also an object. All right? So remember we had so far just a basic directory that had these three files in it, right? This app.yaml, index.yaml, and main.py, which we've been messing with. All right? And the directory is an object, and it's an object pointing to more objects, where these objects are the files. All of these are full instances. All right? So app.yaml, index.yaml, main.py, who are indexed by the fairly long alphanumeric string starting 3d5, 1d3, 038, are all uniquely identifiable. All right? And then we move into the parent part. And the parent part of the commit is how we actually do any form of revision control, how we do some history and things like that. All right? It's not a hard idea to imagine that version control is nothing but a long directed graph. Right? If you are a directed graph, you are a node who has a parent. Your parent, in the case of a commit, is another parent who came before you. That commit that came before you was pointing to an object which was the directory, and we can see how this would go back in time and back in time. All right? All of these commits are unique, but what's a little more interesting is we can observe that in some cases things change, and in some cases they stay the same. All right? So in this model right here, we can see that from between here and here, only one file was changed, whereas between here and here, all three of the files changed. Right? Between here and here, all three of the files changed. So in this case, we actually save some room because these two commits are pointing at the same objects. All right? Does that make sense? So a commit points to an object where an object is an instance of a file, a snapshot of a file at a certain point in time. Okay? So the repository itself is nothing but a blob of all of these objects, all right? And this is what the repository looks like. And so the repository is nothing but a blob of all these objects that are pointed to by these commits. All right? So it's a giant array, a giant hash table, and you index into these hash tables using this tree structure. Everybody with me now? Yeah, this is where it starts to get fun, right? So you can run commands such as git checkout AE635, all right? And this will work because AE635 is going to be a commit object, all right? And that commit object is going to say, all right, I know what's inside of me. If I look at the tree I contain, when you check out this commit, it will take the tree it contains and it will cause the current working directory to reflect the tree of that commit. All right? So all we have to do is we basically move the current working directory to that working directory, 3D4. All right? Everybody understand how it's just a pointer rename operation?
Is it actually making symlinks, or is it actually changing the files in the directory?
So it's actually changing, hard links would be appropriate, or I believe it's actually doing move operations. I don't honestly know. I think it's moves. Actually it has to be moves because hard links won't work, so you edit the actual object files when you edit the files. So it's moves. So it's a lot of rename operations.
Okay.
But renames are really cheap, right? Because when you do a rename operation, the only thing you're actually changing is the inode of the directory it's looking down the files. So you can do them really fast, right? You're not actually copying any data around. Because remember we had snapshots, right? So this whole instance of README, that 038 object, existed in the repository the entire time. So all we're doing now is we are moving it over to here. Okay. So we have a working directory, and we can go ahead and edit these files. We add these files, and we push them back and commit. You end up with a slightly different view of the world. All right? So what actually happened through all these slides? I kind of flew, I'm sorry. We went in, we said we edit this file in the working directory. All right? We add, it changes the index. Where the index is a checked out copy of the current version of the world. When we commit, it copies things from the index back into the repository. All right? Most of the objects remain unchanged. The only thing that happens is now we have a new directory object, or because you have to have a new directory object here, because you're pointing at a different version of the rake file object. All right? You have a new version of the rake file object, and you have a new commit that has appeared as well, a new commit object, to represent this commit you just made. Objects, pointers, everybody with me, because now we're getting into how it works. With a little bit of speed mode, I have to kind of slow down. So I apologize if I kept going fast. All right. All right. So the object model itself, again, is basically you have a commit, and the commit points to a tree. All right, and the commit usually points to the root tree of the old directory, and that tree points to things it contains, which are blobs, where blobs are files, and it points to subtrees, aka subdirectories. All right, so one root tree can express the entire directory as a series of Git objects. All right, and that is indexed uniquely by the commit. Does that make sense? Yeah? Hopefully. Pointer to a snapshot directly with the commit. Look at that. So all of this thing encapsulates one commit. All right. So commit points to the root tree. So it's basically a lot of graphs where a lot of nodes are overlapping. So when we started to look at branching and merging and how that actually works in Git, it turns out that branches are really, really cheap. All right? Because all a branch actually is a pointer to a certain commit. Because the whole idea of a branch is that you want to be able to go and diverge from a certain point in time, right? So if you have a flowing thing if you have history flowing over time, and you want to diverge, and you want to be able to get back to this point, you need to be able to reference the point you split from, all right? You need to be able to find and uniquely identify that commit. Thus, a branch is nothing but a pointer to a certain commit, all right? Branching in Git is done with the git branch command to create a new one, and the checkout branch command to actually jump to it. These two work in tandem, all right? So the branch command itself, we'll go through and we say, all right, this is our repository. Our repository consists of commit number 0, commit number 1, and right now we are on the default branch pointing to commit number 1. Okay? And if I run the command git branch experiment, it means I want to create a new branch called experiment. By default, this new branch points to the same commit as the current branch. You can give it an argument, you can point it to a different commit as well. Right? So right now we have two branches that are both pointing to the same commit. All right? We're still working in the default directory. So if we look and we actually type the git branch command without any arguments, it will tell us that we have two branches in the system. All right? We have one called default, one called experiment, and we are still working on the default branch. All right. If we want to switch to the experiment branch, we run the command checkout, and now this moves the head. All right? The head is this magical thing that is basically always pointing to your current working arena. Usually the head is pointing to a branch, and the branch is pointing to a commit. It's possible to have the head point directly to a commit. It's called attached head. You can do work that way too. But in general, when you're doing any kind of real work, the head points to a branch, the branch points to a commit, the commit points to a tree, the tree points to the contents of the directory, and there's a spider down to go inside it. Sorry. I know there's a children's library once in a while. Anyway, so here we are on our experimental branch. and we make some changes, and we make a commit. All right. Now that we've added a new commit, our branches have officially diverged. Right. So it's not very hard to see how the history works here. The committing process works the same as before. The branch is updated. The branch label experiment is updated to point at this new commit, and we kind of are where we are. We can keep doing this. We can say we want to commit again, and then if we run the command checkout default, then we're just going to jump back to commit number 1. All right, checkout default is relatively easy. All it's going to do is it's going to go through, and any of the objects that have changed in the tree pointers from commit 3 to commit 1 will be copied back over, and now we're back in the state we were a while ago. Okay, and from here, we are free to make other commits. Right, we can have diversion history. This is a hopefully comfortable idea to people who are cool with the idea of version control in general. You can have branches going different directions, doing different things on different branches. All right, so here we are, commit 4. Default points to commit 4 as well. We can go back to experiment. We can check out the experiment. We can commit over there. We have a new commit. We just have history and time, and everything kind of does what we want. Things don't get interesting, however, until you try to merge. All right, as you might imagine, the command in get to merge is merge. Great. All right. So the first thing to understand about the merge command is the merge command will always merge into the current branch. All right. So if we want to merge default and experiment together, but we want to end up on default, the first thing we need to do is hop over to default. All right. You cannot do anything else. Merge will always merge to your branch. Okay. And if everything goes well with the world, we can just say merge. All right. So all this tries to do is this tries to say, all right, I have this commit 6, and I want to merge with experiment. So experiment used to be down there on the bottom, and we're going to hope that everything works out well. But we have this really weird situation in our graph, right? Before we used to be a nice, pretty, clean, linear graph of history, but now we have a commit that has multiple parents. Remember, we had that commit object from forever ago, and the commit object was kind of hanging out and having a good time. So now we have a commit with multiple parents. And it turns out this works just kind of dandy. So when it comes to actually resolving this in practice, the important thing is they do share at some point in time a common history. Right? So it's not that hard to go through and apply the series of differences between these two branches and resolve things. It's not a hard graphing problem to solve. So you can keep going forward. You can create on this experimental branch. Remember, experiment still exists, right? Experiment is still pointing at commit number 5. So you can go ahead and commit number 7 to experiment and keep working forward. And you can go ahead and commit number 8 to your default and keep moving forward. And then we can have lots of fun. All right? And we can say to ourselves, all right, we have this master branch, default branch, whatever you want to call it, the experiment, and you have this common history at C1, and you try and put it all together, and things start to get ugly, right? So what happens between this picture and this picture? You added commit number 6, which was our merge from before. We added commit 7, which is our new branch here, and we have all these parents, and it turns out they all really care, okay? So what's going on here? We have 2 branches that came together over here for default, but experiment kept working on bugs fixed whatever else. So what this really looks like in practice is we have our master branch, which is working through, and this is kind of the thing you're going to push out to the world. This is what everybody gets to see. And this is your experimental development branch over here. And once in a while, you're going to merge in things from the experimental development branch as they start to work. But they can keep working in tandem and just keep going forever. All right? Just because you've merged a branch doesn't mean it ceases to exist, which is unlike other forms of version control. All right? In subversion, when you merge in a branch, that branch goes away. The whole point of a branch was to go try something. Now you're done with it. You don't need it anymore. Well, why keep getting rid of it? You have this nice experimental branch. You can get a very nice history, and you can see what people are doing very well. Everybody with me so far? Yes? No? Maybe so? Boring? Interesting? Hopefully not. Who knows? So you're mostly interested, and the reason you really wanted to use this thing is you wanted to distribute this work among multiple machines and multiple users all over the world. Okay, cool. So now we have 2 local repositories, my local repository, your local repository, and we have the original Git model. All right? And the original Git model was everybody's got a private repository that they're working on, everybody's got a public repository that they push to once in a while, and everybody just grabs things when they want it. This is the nice dream. This is not how it's used in practice, but this is what it was originally designed with. All right? So I have my local repository, I've made changes A, B, and C, and I push them to my public repository. And I maybe send an email, I maybe announce to the world, maybe my post-commit hook sends an email, who knows? And anyone in the world who says, damn, I really want A, B, and C, goes into my public repository and they fetch them. And they go and they grab the changes A, B, and C, and then they can apply them to the local repository. And then you, having had changes A, B, and C, can keep going out and being like, oh, I'm going to do D, E, and F. I'm going to push that out to the world. And if I want to get it, then I have to fetch it from you. All right? Great. This sounds like a nice model of the world, but it turns out to be a lot of work. But before we get too far, we can come back and we can see what happens if there's multiple people. All right? It's not just a two-person world. It's a lots-of-person world. So I have my repository, and now we start getting into a little more concrete Git terminology, right? So my repository it has the commit, which is pointing to, why did I change the color scheme? It's pointing to a tree, which is pointing to a pair of blobs, all right? So what this really is, my repository currently consists of one commit that has a directory with 2 files in it, right? Everybody see how that works, all right? And that's called the master branch. So the master branch is pointing to the commit 5EC, and everything is kind of hanging out there. So that's my commit, that's my tree, those are my blocks. And I can push it out to the public world, all right? And then my developer, Nick, can grab a copy of the project we're working on, and he can have it, and he has the same things I have on my machine. And he can go ahead and he can commit a new change, all right? So let's dig into his change a little bit. We've made a commit, all right, and how many files did he change?
Just one.
How do you know?
Because the tree still points to the old second object. There's only one new object.
Exactly, there's one new object, all right? So what we know is we know that he has edited one file and left the other one alone, right? Because you still have a commit pointing to a directory pointing to 2 files, all right? And the first and second trees are both pointing to the same blob for one file and a unique blob for the second file, right? So we can see exactly what he did just by looking at what Git stores in the world with me so far. Okay. So my developer, Jessica, she can also grab things, and she can also make a change. All right, so what did Jessica do?
She changed both.
She changed both, all right? Hopefully people can see how they did that. And then Nick and Jessica are both going to push out to their public repositories, all right? And then it starts to turn out this is kind of a pain in the ass to keep organized, right? So you can do some things to help yourself out. Right? So when you're working on projects like this, and you all have public repositories where you're working, you want to have nice labels and nice names for everything. So Git has this notion called remotes, all right? And it turns out really what's going on is there's not that much of a difference in practice between this repository and that repository, right? They look very much similar. They look less similar. They look very similar. One just has a little more data than the other one, all right? But they share a very common history, and all these nice unique hashes hash the same no matter what machine you're on. Okay? So what we can do is we can have basically remote tracking. So what we're going to do is we're going to say, most of the repository I have on disk, all right? But I'm going to add this remote repository that should look a lot like me. And I give it the nickname Nick. So I've added the remote named Nick. It's hanging out over there. I can do the same thing for Jess's repository. She hangs out over there. Great. And then I'm going to run what we call the fetch operation. So the fetch operation basically says, I have this cached version of the repository on my disk full of objects, references, all that stuff. And Nick has this version out on his disk. And I'm going to fetch it. I'm going to fetch all the additional objects in Nick's repository that are not in mine. Fetch does nothing else, all right? So you'll see what happened here is down in my repository, nothing's changed, right? I have my master, which is still hanging out here. I have the original remote I created called public/master that I pushed out to public, sorry. And I have these new objects that are just hanging out, all right? And they're there, but I haven't done anything with them. There is new objects that are hanging out in my tree, all right? And when the Git will put it all together and figure out what's going on. So we can do the same thing, and we see that after we have pulled in this, we have this new branch called Nick/master, all right? So what we're doing here is we're identifying that by default, we have my machine, which is hanging out on its own, there's no path or anything like that. We have the remote machine called public I push to, we have the remote machine called Nick I push to over here, all right? And Nick's current head is pointing right here, the beginning of this branch is pointing to this commit, which is why Nick master points there. Meanwhile, I've made no changes, so I still point here. Okay? So it gives us a nice naming scheme to refer to everything. Do the same thing with Jess. We can grab her commits. Okay, great. She's made this one commit. And much in the same way, we end up with the branch named Jess/master. So now we have all these branches. All right? By fetching, we have fetched not only the blob, tree, and commit, we have also fetched the branches. Remember, branches are just pointers, so we have all these nice names that point to things. Everybody with me? So. Okay. Now's when things get fun. Git merge, we recall, what it does is it will merge into my current branch all the other branches I list. I can list multiple branches. Alright, so what I want to do now is I want to come up with the net commit of everything that Nick has done, everything that Jess has done, because I'm going to publish this project to the world. Alright, so we can do it in one go. And as long as there's no conflicts, we'll deal with that later. As long as there's no conflicts, everything's great. Alright, we come up with this new commit at the very end. Alright, and this new commit is the result of the merge. Alright, so why do we need a new commit there? What happened? What is the difference between 2FB and B3B?
It's the combination of the repositories. And you're pushing it to the main
The end result is that none of these trees were sufficient to express the result of the merge of Nick's and Jess's changes. So the merge operation itself had to create a new tree. I don't think I had to change any blobs to essentially end up expressing the result of the commit. Does that make sense? All right. So this is what happens when you have a merge that actually creates a new commit, and it creates the information, lets people know where it came from. You have history. So that merge has parents of the C12 and 2FB, right, and 5EC. It has all three as parents, because I merged my branch with Nick's branch, Jess's branch. And then I can push it out to the public, and the public all have it, and they can all enjoy it. All right, and we can kind of see where everything tracked around, right? So we have all of Nick's changes, which started on Nick's machine. He pushed to the public world. I brought down to my repository, and then got pushed out during that operation. We can see all of Jess's changes, which had much the same thing going on, and then we can see the final result of the merge, which I had to do on my machine. All right. So what I kind of alluded to a second ago is this notion that remotes are nothing more than branches. All right. Remotes are one of the more complicated things that give a lot of new people with Git trouble. Things that aren't working correctly usually are surrounding this. But if you start to think of them as a branch, they start to make a lot more sense. So you have my machine, where I, the talker, am Scott, and you have Jessica's machine. All right. And Jessica clones my repository. When she clones my repository, she ends up with the branch Scott/default, because that's the default on my machine, right? So this branch and this branch are the same, it's just a different name, okay? And these are what those refs we talked about earlier for. Refs are references to branches and keep track of this naming scheme, because the two branch objects have to be the same, but they're named differently depending where you are, right? And then she has her own default depending on where she is hanging out, all right? Oh, look at that, I'll just let the slides go. Anyway, so she goes ahead and makes some changes, all right, and this is where her branch ends up. But we see that I haven't made any changes in my machine, or even if I had, she hasn't fetched them yet, so she wouldn't know. So I go through and I make changes, but as far as Jessica knows, Scott default is still pointing to commit 1, because she hasn't fetched any of the updates from me. She doesn't know things have changed, all right? So she runs the fetch operation. The next thing she realizes is that the Scott branch has moved forward. So fetch will fetch commit 5, 6, and 7, and it will fetch the new branch and will tell her, update your view of the world to look like this. Okay? We can extend this idea to bring in a branch of Jessica's, all right? But if we want, whoa, what are we doing? What are we doing? What are we doing? Oh dear, it's going so well. Sorry, this is the flaw of putting someone else's slides. Okay. Oh, I'm running on Jessica's machine, and I can basically do anything with it. If I want to create an experimental branch to do some work of my own, I can do that. If I want to merge in Scott's branch to bring in all the changes from the other developer, I can do that as well. That's all that sign is doing. It's really confusing to put it. I'm sorry. And the whole idea is that a quote-unquote remote branch is nothing more than a real branch, which is just a pointer to how things used to look the last time you fetched. All right? This is really, really cool. All right? Because it lets you just go out and everybody gets to do their own work. All right? You're not fighting each other for access to the repository. You're not updating all the time, and you can do a lot of work on your own. All right? You can go through. You can clone code with some projection. All right? You can make a branch to fix issue 53. Great, fine. You get some work done, and all of a sudden, a fire goes out, and the brand new issue 102 is absolutely mission critical. All right. So you can check out the production branch. All right. All your changes that you were working on for issue 53 can just kind of hang out. You create a new branch for that issue. You fix the issue. You check out production. You merge the issue back in, and you go right back to working on issue 53. Hopefully people get an idea of the workflow. You can hop around from branch to branch. It's very free, it's very cheap. You're encouraged to move from point A to point B. All right, so this is the pictorial view of the world. You had production, you checked out a new branch. All of a sudden, shit hits the fan. So you check out a new version of this branch, do a little work, merge it back over. I'm working out there. I've posted the changes, and we'll keep working on issue 53. You can work on issue 53 a different way. You can do whatever you want. This is the beauty of version control. The whole idea is it's really fast and it's really easy. Hopefully people are maybe slow. All right? So going back a little bit more to how Git works, going back to this model again at the very beginning, and we expressed last time that deltas were stored in previous repositories, whereas in Git we store all of these actual instances. All right? So when you're interested, one of the most powerful things in version control is you get a command, something to the effect of diff. All right? Diff's really cool because it tells you what's going on in the world, and it says, I changed hello world to hola mundo, and we're happy about that. And we can go through, and right now, by default, git diff will tell us what has not been staged. All right? So git diff will tell you the difference between the working directory and the index. If you want to know what you have staged because you've forgotten what you're about to commit, you can say git diff cached, and we'll show you that. Are people familiar with diff, how it works? I'm going faster in this part of the talk again. Yes? No? Okay. So diff basically goes through and finds the differences between two files. Hopefully this picture was a relatively clear idea, wherein we had the file main.py. Long ago in the talk we added this comment. We took this line and removed it and replaced it with that line. It gives you a nice view of the world. The unified diff basically says we've done it to this file in about these ranges. And it's basically the heart of all version control, is what's changed. All right, so git diff lets you see. And again, we talked about in the beginning of the talk, you had this working directory index repository idea. So if you have things that are changed but you haven't staged, you can see them with diff. If you have things you've staged but haven't committed, you see them with the cached command. Otherwise, that's how the world works. Diff burn patches, patches go back in. You can apply patches. It's version control. Maybe you wanted more out of that, I don't know. If you did, I could talk about that. Last but not least, there exists the command git log. Git log does exactly what you want it to do. All those commit messages that were so helpful and useful, you can go through and see. And this should hopefully look familiar, because git log, all it has to do is look at the commit objects themselves. All right, git log is very fast, because it basically goes through and says, I find a commit object, I find the parent, I keep finding parents, I print the commit object, I print its parent, etc., etc., etc. All right, so that's me, that's my parent, that is the commit ID. These are all things that are stored within it. All right, if you want to go through and you want to find how things have changed between where you are, you can look at the log of a certain branch. You can look at the log of the original branch. You can look, at the log of the original branch, of the origin. You can look whatever you want. Sorry, I'm trying to run over time, so really sped up. I have like 10 slides? Yeah, 10 slides. All right. Git has really, really nice built-in help. It turns out to be really powerful. If you have any of these commands, you don't know how they work, git diff, git log, git whatever, you can toss help on the end and things will work. On the flip side, you can do git help. It basically does what you want. This is where you get git from. It turns out where you get git from is full of lots of great documentation, tells you everything you might possibly want to know in the world, and it has this really cool thing called the Git book, actually kind of a relatively easy read. You can read it in chunks, put it up, put it down, find out cool nerdy things about Git as you go through it. There are varying degrees of tutorials and references. There are even Git videos you can watch if you want to have even fun with those. And there are Git flashcards, there are Git everythings. But everything you need to know about Git to be effective, there are 12 commands. They are initialize, clone, add, commit, branch, checkout, merge, remote, fetch, push, diff, log, and that's it. All right. And that's actually it for the entire talk about Git. So when you're talking to Git, a few resources out there. Again, the website, Gitcast, where you can find podcasts of Git. You can learn from GitHub. They have nice tutorials there. They have an IRC channel. Who doesn't? And Pete code is actually dead, so I'm going to take this out. Okay. I apologize, I ran about 6 minutes over what I was going for. Hopefully it was interesting. Hopefully the bits on how Git worked were a little bit more interesting. It was kind of a mixed bag on who knew what they were doing. Hopefully I didn't go too fast to kill anybody. And I hope you all had fun.
Thank you.